Thank you all. Thank you for joining the session today. So we are going to discuss about the high-speed design tools in Altium Designer. So myself, Manimaran, I'm working as a senior field application engineer for Altium. So here is the, for the upcoming webinar, please do visit our website, VVDN Tools. So under the events page, you will get that details for the upcoming webinars. So you can register for that. And we are also available on social medias like Facebook, YouTube, and LinkedIn. So please do follow us. So here is the agenda for today's session. Like we are going to see the overview of high-speed design, like what is high-speed designs, and how we can define high-speed signals in Altium. Like basically, we are going to see what are the what options or features or the tools we have in Altium Designer if we want to develop an high-speed design, high-speed board or high-speed designs, right? So how to configure the high-speed design rules and vias, and what means for the impedance and return path management, and we will go through the what routing options we have in Altium, routing and length matching options, and signal integrity analysis. Of course, if it is a high-speed design, we should do the signal integrity analysis, right? So, and much more. So like we will see some other options also, which is related to high-speed designs. And finally, if we have some time, I will show the demonstration of the features what we are going to discuss, right? So in the end, we will have a question answer sessions. So I will answer your questions. And meantime, in between, if you have any questions, you can just put it in the chat window. So I will answer to your questions in the end, right? So first, what is a high-speed design? So this is just a definition. I just put it here. So generally, a high-speed PCB design is like any design where the integrity of your signal begins to be impacted by the physical characteristics of your PCB, okay, such as layout, packaging. It can be the interconnections or the layer stack up and so on. Like this is a definitions. So basically, we would say like if we have any high-speed devices or high-speed interfaces in your PCB design, that is a high-speed PCB design. It means that is a high-speed design, right? For example, I have mentioned DDR, PCI, HDMI, Ethernet. So these are all the high-speed interfaces. So if you are developing any board or any PCB with these interfaces, so we call it as a high-speed design, right? So apart from that, in depth, technically, if we speak, then a design is a high-speed design when it includes the devices with fast edges. You know that signal travels fast. Okay, we have the devices with fast edges. Means it switches the state so quickly. Okay, so like from 0 to 1, if you say, like it will switch the state quickly before reaching the destination, right? From if I'm sending a signal from source to a destination, okay, from source component to destination component or IC device, in between, sorry, in between, if it if we can change the state quickly without reaching the destination, so that we call it as a high-speed design. So yeah, here you have the definition. So like devices that switch the date so quickly that the transition is complete before the signal can travel along the route and reach the target pin. Okay, so that's what we call it as a high-speed device. You know, we mentioned like what are the high-speed devices or high-speed interfaces, and when we call it that as a high-speed device. So we have a definition here, right? So if the signal can switch the state so quickly, then what issues we will face? Like signal reflect back to the source. We will call it as a reflection, and like yeah, we will not get the original signal in the receiver, and we will face because due to this we may have EMI issue on the crosstalk and many other issues that what we will see in the next slides, right? So basically now you've got some idea like what is high-speed designs. Okay, so the next slide is what are the challenges we have or what needs to be considered if you are developing a high-speed design. So what are the challenges is there, and what are the considerations you have to take care, right? So basically, means all the high-speed designs, maybe you should use that microprocessor or fine-pitch components. So how I'm going to fan out those signals, and the routing, like if you have a high-speed signal, so how I'm going to route the signal. Because if you search it in Google, like for all the like high-speed design guidelines, there are a lot of guidelines. So how to route the signal, how to match the signal, and even if you have any FPGA or controller components, controller devices for the high speed design, uh, for the data sheet itself, they would have mentioned, they have mentioned the guidelines, like how to route, how to fan out, how to place the component TCAPs. So there are a lot of guidelines, right? So to achieve the guidelines, we should have some features, so that we will see. Okay, and yeah, of course, we should take care of the material and layer stack. So if you are handling with high speed, so what material I have to choose, and what layer stack I have to follow. So, and how to avoid the reflection. So these reflections, as I said, if the signal is switching the state quickly, so you will face the reflection. And if you are not following the impedance, then you will face the signal will get reflected back to the source. So we need to take care of the reflection and EMI issue. As I said, even if it is high speed, you should have, means for all the signal you should have a proper return path. But for high speeds, you have to take care more, right? So there should be a proper return path, and you should avoid the noise and crosstalk by defining the rules. And if there is a via stub and via impedance mismatch, so that can affect the signal noise. Okay, that means that can affect the signal. And I think crosstalk I have mentioned already, sorry. And signal skew. And your board, finally, your board should be manufacturable, right? So we need some rules to verify the manufacturability of the design. Okay, so these are the challenges we have, and these are the points to be considered if you are developing a high-speed design, right? So next, so how to tackle each of the challenges in designing a high-speed PCB? Okay, so generally to avoid the reflection, you should have the termination components. Okay, and you have to place the termination component, and you should have options to define the high-speed signals and rules for that, and how I'm going to route the high-speed signals with a controlled impedance. In this impedance where will come if you are handling a high-speed design, because everything like depends on the means the issues what we have seen in the previous slide, like EMI, crosstalk, reflection, noise, everything is based on the it's a track width, right? Routing impedance and the length matching. So they both are means you have to consider this and properties and dimensions of the board materials, and layer arrangement, how you are going to arrange the layers, because you have to take care of the reference plane, right? So if you are routing the signal in top layer, so what will be the reference layer for the return path? Okay, so that kind of management. And then configuration, how we are going to configure the vias, and routing differential pair, how we can create the differential pair. If it is a high speed, generally you should have the differential pair will be there even for USB and it's Ethernet. Okay, so then yeah, we should have some manufacturability option. Finally, I have developed my PCB or I have completed my design, but how I have to make sure that I don't have any issues with the signal. So we should have some feature, right? So we have signal integrity simulation. So we are going to see all these options, what tools or what features we have in Altium in the next slides, right? So next, defining the high-speed signals. So I started my design. Yeah, you have to make sure the placement and all. Okay, yeah, because there is a guideline for the component placement if it is a high speed. Generally, the component placement is based on the mechanical enclosure as well as the what we can say, the interfaces, like where I'm going to keep the interfaces, where I'm going to keep my processor or FPGA or controller. Okay, so that depends, like, because you are developing a high-speed design, so you have to follow the guidelines. And if you are not following the guidelines, or if it is affecting the signals, it can be a signal length or impedance or anything, right? So we have to take care of everything. So after the placement, what the next step? So I have to define the high-speed signals as a bus, so that I can easily highlight the nets, and I can plan for the means what we can say routing flow. You can enable the particular buses or classes, and then you can see the means routing planning you can do. So we have an option called to create a net classes in Altium, and yeah, we can create a differential pair automatically, automatic differential pair creation also there. You can do it manually. We have directive option that I will show it in the demo. Okay, so we have a differential pair creation option and X signals. Many of you, I mean, some of you may aware or some of you not aware what is X signals. In the right side image, you can see this is a okay. Consider it's a clock signal, right? So this class signal is connected from one component to another component, and in between we have some resistors, termination resistors. Consider, okay. So there are three components, but if you in schematic, you may be connecting this like from this blue color, this right side, this component to this resistor. The net name is different, and from this resistor to the processor, the net name is different. It cannot be same, right? But to match this signal, from my point of view, I have to match the signal from source to destination, right? Not from source to in between and in between to destinations. So that will not consider this propagation delay, this resistor propagation delay, right? In between we have some component. So this XNet is nothing but source to destination. In between we have one component. So source to in between component called net 1, and in between component to destination net 2. So we are merging this net 1 and net 2 as a single net. Okay, that is called XNet. Maybe you can Google it, or you can, if you type in X signals, so you will get some definition and some examples. So for better understanding, right? So if it is high speed, then to match this length, I need X signals. So we have this X signal wizard option. I will show you. Okay, and the topology. Yeah, so if it is high speed, how I'm going to route my signals, right? See, for example, here, this is like, it can be a daisy chain topologies or T topology. Okay, consider you have one processor and two DDRs. Okay, so now I'm going to match I'm going to route the signal and match the signal from source to one DDR and the next DDR. That is daisy chain topology. Okay, I thought of adding that images, but I forget. But you can make a note and you can Google it. You will get a lot of image or references for the topologies. Okay, E topology and daisy chain topology. So daisy chain topology is nothing but you have one processor and two DDR. From processor to first DDR and second DDR, if directly it is connecting, that is daisy chain topology. And from processor to these two DDRs, if it is, you have some midpoint and connecting both from that midpoint, that is called a T topology. Okay, so for the routing or the length matching, we should have this topology same. So we have this option in Altium. Okay, if you are already developing a high speed, maybe you can explore this. Okay, you can try to use this feature. And if you are like about to create, or you are planning to create, or you are learning to develop a high-speed design, then you can make a note and you can just explore it. Okay, like this topology and all will come. So, and anytime you can reach us, we will be there to explain and give the demo or support, right? Yeah, so we have defined the signals now, and how to configure the the rules and wires. So I have defined my signal. Now I have to define the what we can say rules. Rules in the sense, what is the track width I'm going to follow? What is the clearance I'm going to follow? That should be as per the impedance. I have to follow the impedance, right? For example, if it is a USB, it's a 90 ohm, right? 90 ohm impedance. If it is a DDR, it's 100 ohm impedance. So we have, for each high speed signals, there is an impedance. So we should follow the impedance for the proper signal transmission from source to destinations, right? Without any reflection, crosstalk, or means any loss. So, so this impedance profile we can assign. We have an option to create the impedance. Okay. So for the track width and clearances. Okay. For single-ended and differential-ended, we have. So we can just configure it in the first image, in the top side image, the right side. You can see, right, use impedance profile. So single ohm you have we are assigning here. Same for the differential pairs, 100 ohm and any impedances you can calculate and you can add it here. And properties of the routing is nothing but like what is the trace width and how I'm going to route, like whether the what we can say, the angle of the routing. If it is high speed, we will not go with a 45-degree or 90-degree, right? You should go with some based on the frequency or based on the speed of the signal. You should go with arc routing, right? So you can, that is a property of the routing. So we can change the property of the routing in the properties panel that I will show you to you. And yeah, pin package delay. So we are routing the signal in PCB, and we have option to match the signal in PCB, right? But already there is a pin delay. If they are developing the processor, I hope you are aware that inside there is a routing, right? So already there is a delay for each pin. So if I have to match the signals, like if it is high speed signal, there is a guideline. So all the signals should be means maximum 1 inch, maximum or minimum 1 inch, or not more than 1 inch. Okay, 1000 mils, and with the tolerance, some 5 to 10 mils tolerances, right? So outside the track, we can match it. But what about the pin delay? Already there is a delay within the processor, within the package, right? IC. So we have an option to include that delay as well to your length matching. So we can add the pin package delay. So it will be accurate, right? And maybe I have not expanded this, but there is a high-speed design rule. What are the high-speed design rules in Altium? As I mentioned before, if you are handling high speed, you should check the return path, you should check the parallelism, length matching options, and topology options. So there are some rules we have for the high speed that I will explore it in the demo. Okay. And then via configuration, the right side means down, you can see the second image. So when we go for high speed design via sizes and whether we are going to use micro via, laser via, or blend and buried via. So based on the board shape and based on the signal, okay, we need to configure the vias, because by mistake, means suppose if you are using a through hole via, okay, and the signals are you have routed the signal from top to in between layer, okay, in between the via, you have used the via from top layer to inner layer, okay, and from inner layer to bottom side, the via copper is there, right? That will act as a stub, okay, that create an issue in the signal integrity, okay, so that we have to avoid. So in that case, either you can go with blind vias or you have to back drill the via. So we have an option for back drilling as well as blend and blur via configurations. Okay. So next, impedance and return path management. Okay. Yeah. So we we discussed we have to follow the impedance, but how I can calculate the impedance, right? So in that sheet they mentioned I have to follow 50 ohm impedance, 90 ohm impedance, 100 ohm impedance, but how I'm going to make sure that I'm following the proper impedances, right? So there is a formula to calculate that based on the track width and the copper arms and the reference plane dielectric height and the nearby signal. So there are a lot of steps to calculate that. So, but in Altium, you don't need to worry about that. Based on your stack up, in the right side top images, based on your stack up material and copper thickness, you can simply mention the value of the impedance, which impedance you are going to calculate. Automatically it calculates the track width and you can play with it. You can just adjust based on your requirement, right? So we have an inbuilt impedance calculator for single-ended, differential-ended, and also RF. In the latest version, RF also included. Okay, so you can RF, you can calculate the impedances with this impedance calculator. No need to do the theoretical or this formula and all you don't need to use. Okay, and power plane. Yeah, we are talking about return path, right? So you should have a proper ground plane or power plane return path, right? So yeah, in Altium, in the layer stack itself, you can define that whether you are going to follow the plane layer or a polygon layer, right? So if you assign the plane layer, it is very easy. It will be like a complete plane layer, and you can simply assign the net to that, like whether it's a ground or not. And if you want to split the plane, like I have a design with multiple powers, okay, then you have to split that powers, split the plane with different powers. So you can do that with a split plane feature. And polygon. So if you don't prefer a plane layer, and you can always use this polygon layer, because in Altium, plane layer is a negative artwork and polygon is a positive artwork. So if you're not familiar, or if you're not okay with the plane option, then you can go with the polygon. And there are a lot of polygon actions, like you can merge, you can subtract, then you can adjust the polygons, edit the change the corner of the polygon. So a lot of polygon actions is there. It will help you to quickly create the polygon shapes, and you can provide the reference planes, right, with the help of polygons, right? And then yeah, I have power plane and I have polygon, okay, in my layers. I kept it and I have completed the routing. But how I can make sure that my return path is proper, my signal is not traveling on void, how I can make sure? So we have a rule called return path rule. So you can just once you completed the signal, okay, you can define the signal for which signal you want to check the return path, or complete PCB you are checking the return path. Because sometimes if the board is very dense, we have to we cannot verify the return path for all the signals, because in some signal may actually you should avoid, but worst case, right? In that case, maybe you need some option to check the return path only for the high speed signals, because we have this, because maybe if you want to verify for all the signal, it may take some time. If you have the number of layers are more, or it's a very big design, right? Instead, you can simply assign the rule for particular signals, and signal wise, you can check the return path. So that will be easy, right? So in the right side of this image explains that we have selected the net class only for the data nets. I'm checking the reference return path, and reference plane it will take automatically as per the layer stacker, right? So next, okay, rules I have defined, and then bias are defined, and I have defined the signals. Now I'm going to route and match the signal. I have to complete my routing. You have an Altium for the differential routing and length matching, right? So basically, interactive routing is there by default, right? Normal with the other tool also, like you can simply route it manually, or you can use active route. Active route is an interactive automated routing, right? You are defining the flow, where which way the path, how the signal is going to route, how the planning, flow planning we used to say, right? So from this processor to the DDR or any signal, I'm going to route on this path. Another signal I'm going to route on this path and this layer. So this active route, you can able to define the layer, signal in the routing path as well as the layers, and also automatic tuning you can enable. So based on the constraints, it takes the track width, clearance, and the tuning, matching, length match, target. So it automatically complete the routing based on the flow, how you have defined. Why we are saying it as an interactive automated routing means it needs some inputs from you, like how you are going to route the signal on which path, or what constraints has to be followed. So that's why we are calling it as interactive automatic routing, right? And also this is just an example. I put it here in the right side. This is image, like we have different options for the tuning, okay, from rule or from net. So you can change it. And the corner of the serpentine means this delay tune, okay, think we used to say serpentine delay tune or tuning. Okay, many names are there. So whether you want it 45-degree or arc routing, so that can be changed. Okay, and once you reach that, once in Altium there is a good advantage. Like once it is reached the target, it will highlight this color in the this is the green color. The right side you are seeing there. Maximum reached. We have reached the rule. As per the rule, we have reached the maximum length. So after that, it will not allow you to increase. So by mistake, also you don't need to manually adjust and verify. Okay, so that will be easy for us. And match with respect to delay. In 20 versions, we have introduced this. You can match the signal not only with respect to length. Okay, what is the maximum length? You can match the signal with the like a delay second. Okay, so yeah, so signals travels in light, so you can means speed, so you can use that. You can match the signal with respect to delay, right? And I will show you the length matching and tuning and routing tools in Altium. What all we have during the demonstrations, right? And finally, I have completed my PCB routing. Everything is completed. I want to do the signal integrity, right? I have to make sure my signal is traveling from source to destination properly, right? I'm not facing any signal integrity issues. So this signal integrity simulation feature is comes up with a base package. So you don't need to pay extra amount to means for the signal integrity simulation somehow, right? And in Altium, we have pre-layout signal integrity analysis and post-layout signal integrity analysis, which means only if you have if you are not developed the PCB, so only with the semantic, I want to do the simulations, right? For example, means PCB is in development stage, not yet started, but I want to make sure the signal integrity analysis with some input like approximate value, what will be the maximum length of the signal, what impedance I'm going to follow. Okay, and means by defining this as an approximate value, I can able to do the simulation pre-layout signal integrity only with the semantic. And once I completed my PCB, I can do post layout signal integrity analysis. Okay, with the actual track width and track length, impedance, and everything. Okay, which wire I have used. So everything will be there in the actual PCB layout, and that is called as post layout signal integrity analysis. So Altium supports this both the pre and post layout signal integrity analysis, right? And this is an image like termination without terminations. The top without termination, with the termination. This is a reflection image, and in the down this is a crosstalk image from source and destinations, right? And sometimes this is a rare case. So if you are not able to complete the routing, okay, and you need to swap the IO signal. Okay, this is a worst case scenario. Like sometimes we will face if you are developing a very high board, even in sometimes in between the DDR signals, you have to swap the signals. Okay, you know, in the right side down, you can see the issue. The first image, there's a crisscross. So I'm unable to complete the routing until unless if I use the wire. But if I use the wire again, if it is a high-speed signal, then I have to means to take care of that wire step, and there are a lot of wire impedances. So everything I have to take care. Even the wire annular ring also affects the impedance of the wires and then the signal loss, right? So in that case, if it is acceptable, very few means I think you need to verify with your hardware engineer or software engineer whether we can swap the signals or not. Okay, based on the component or based on the configuration, because they have to do some configuration for the programming and all. So you have to verify with them. If that is acceptable, you can always configure the pin or part swapping, okay, in the library itself, and that can be in the PCB. You can just means implement it. You can apply it, right? Okay, this will be helpful for your high-speed designs. So next. This is just like if you are developing a higher complex designs, right? This is an example design which is available in your installation folder if you are an Altium user, right? So for a complex design, you have means we are supporting with the hierarchical semantic design as well as the sheet symbol, and this it will be easy for the reviewer to verify what interfaces are there, and what are the buses are connecting between the processor to these interfaces. So it can be easy to verify with this kind of uh, design features for a complex design, right? If you have 100 sheets, sometimes 60, 20 sheets also more, right? So you can define that hierarchical design, like what is the main top level sheet and which is under the child, and what is, for example, here in the C, you can see under power, all the power semantic sheets are there. Like that, you can make own high speed interfaces. Under that, you can keep the interfaces. So like that, it will be easy for them to verify as well as the understandable, like, and design wise it will be very easy to create the classes and other. Okay, so let's go to the demonstrations. So if we have some time, I will just show that what features we have discussed. Okay, I hope my Altium screen is visible to you. Can anyone confirm in the chat window?
Yes, visible. Yes.
Yeah. Okay. Thank you. So yeah, this is as I said, this is an example board file in Altium. Some other board design. You can see this is the hierarchical design under mini PC. This is a functional diagram, right? So you can see we have used harness here. So a reviewer can easily understand. So these are the bytes, and they have connected from this processor to this semantic DDI4 semantic component. Okay, and from here directly you can open the semantic of this. Okay. These are the directive for creating the differential pair. So suppose if you have 10 to 20 differential pair in single shot, you don't need to place the directive for all. Simply put a blanket. Okay, place the directives blanket. You can select this number of signal and place only one directive. Okay, it's not the right example. I'm just explaining. Okay, and this is a harness connector, so you can just select the signals and make it as a bus. It's a next level bus line. So this will be there here, right? Yeah, this is just an example, and I just want to show you the starting, like, 1 minute. So open on PCB. So basically, we need means impedance and routing option, length matching option. So what features we have, what are the tools or features we discussed earlier in the session? I will show you now. Okay, let it open. It's a big design, so it takes some time. Yeah, and yeah, here you can see in this image interfaces images also you can put it for means for our understanding, right? Yeah, so this is a motherboard design. Okay, first I just want to show the stack up. We'll go with the material and this one. So design, layer stack manager, or if you want to go with the flow. So first I have completed my placement. Okay, based on the interfaces or based on the mechanical enclosure. So after that, what I will do, I have to do the net classes, right? So you can go to design classes. You can create classes here. Okay, new class, art class, and you can just you can select the signals which is related to the class, like each byte you can select it, right? So 0 to 7, 1 byte, and mask and store. Okay, so you can create a classes for this. So once you created the class for all the interfaces, so you can go to the design rules. So it will be easy for you to create the width of the width for the signals, right? Means a track width. So here, I think in this design that we haven't followed the impedance profile, but if you have called these track width and all, they have mentioned it from the manual calculation, or they got it from the fabricator. But if you calculated in the layer stack manager, as I mentioned, we have our own inbuilt impedance calculator. So if you calculated the impedances, you can use this impedance profile and select the signal net classes, assign the impedances, right? Even for differential pair also, differential pair routing, even for differential pair also, you have that option, impedance profile, okay? 100 ohm impedance, 90 ohm impedance, you can simply select it, right? So we have selected and we have assigned the classes and routes. Now clearances can be assigned. I think we can avoid this means a number of clearances rule. Okay, we will plan for that session. Okay, because last time we have covered Altium query in our previous webinar. If you heard about that, how to use the Altium query language to minimize this. Like, see here you have for the same DDR byte you have 5 clearances rule, but if you use the query, you can make it as a single clearance rule. Okay. So if you go through that webinar, you will get some idea how to use it, and we will also plan for a webinar in future, right? And then next, so some of the high-speed rules for fan out, again you can go with the default, okay? And if it is any for particular BGA, you can put a room over there and you can create a room for that. So these are the high-speed rules here. Parallelism, if you want to verify whether the signals by means, for example, worst case, you have 2 signal layers adjacent to each other, right? Basically, we should not go with that, but in worst case, we will go, right? Means signal layer next should be the reference plane layer, but sometimes we will have one more signal layer adjacent to it, right? In that case, we should verify the parallelism, because parallelism again affects the signal, right? So we have a parallelism option, and so like this. So what is the maximum length is allowed for parallelism, and length matching signals. You can define the maximum minimum length for the target, okay, with the tolerance, or group matching. So if you are following the some group of signal tolerances, okay, all this group of signal should be in the same length with some tolerances. So that is group matching, and this is like particular signal or classes should be in the maximum length of the signal, maximum allowable length with the tolerance. This is group of signal with the tolerances. And then stub length, as I said, you can avoid this stub length, okay? And via count, if it is a high speed, you should reduce the via. You should not use the via, or you should reduce the via. So you can use this rule to define that stub length, backtrailing, VZ, right? So you can define the backtrail value and all, and then return path. Okay, you can select the SNIT classes and you can verify the return path for that. Okay. Yeah, so next I'll go to the stack up and show you how we can calculate the impedances. Okay. And we have a material library so that you can easily select the libraries, because many of you know that we are going with FR4, right? But when it comes to high speed, so you have to select your material. It can be different material type, right? Not FR4. Some other materials also there, Roger and that I forget that name, but means other materials for high speed designs, you have to follow the material name, right? So you can select it from our material library, and you can create your own material library based on your manufacturer. You can get the details from them, okay, from this material library. So for each type, you can just add it here, add your new library, okay, mention the values, and you can add the value. Keep it as your material library, okay. Even surface finishes, copper, solder mask, everything you can add as a library, okay. And as I said, if you go to this is a roughness. I forgot to mention the high speed. If you are developing a high speed board, Even the copper surface roughness, okay, affects the signal. Means, I mean, it signal loss, or it affects the signal, right? So in that case, you can mention the roughness of the material conductor, and you can calculate the, I mean, based on that, it gives the impedance. Okay, because this roughness affects the impedance only. So next we will. Yeah, so here in the down you can see impedances and wire types. So first we will see wire types. So here is the through hole wire. If you want to add blind wire, so you can add there like this, and you can change the layers from 1 to 5 how you want the blind wire. So there are you have the configuration for blind and blind wire, even for the back drilling. Okay. So back drill wire, you can mention the back drill wire sizes and impedances. Impedances, you can add the impedance profile simply, and here you can see it gives the track with value for the selected impedance. This is a single-ended 50 ohm impedance. You can change to differential 9000 or coplanar for RF, coplanar and single and differential, right? And yeah, if you select any impedance, it will display which reference it took for the calculation, right? And here you can able to see the calculations of width and what is the delay, inductance, capacitance, all the details you will get it here, right? And then for routing, if you go to route, interactive routing, manual routing is there, and active route is there. Okay, active route is you can use tune selected, so automatically it will complete the routing. And we have conducted a separate webinar for this active route, so I'm not going to explain in depth. Okay, you can select the layers and you can use this tune selected, so automatically it will complete the routing with the route guide. Okay, please watch our active route webinar, so you will get some more ideas on this, right? So we have active route feature and tuning features, right? So next, so we have completed the routing and the length tuning, right? You can see like this. Okay, selecting the IC. So if you want to change the signal, okay, let me show just an example. Okay. So in the right side, you can see it is displaying the length of the signal, right? Length gauge we used to see. And if you press tab, you have all the control here, which layer you are routing and what is the corner style. You are going with any angle or arc routing and all, right? And gloss effect. You are enabling the length gauge or not. Show length gauge. Okay. You can use this. And yeah, pin swapping. That I will explain later. Okay, return path we discussed, length matching, and yeah, part swapping. In here I have to open the library. So this part swapping, if you want to enable the pin swapping or part swapping, that has to be done in the library itself. Means the semantic symbol library itself, you have to enable that pin or part swapping. Only then you can do it in the PCB, right? Okay, I don't have any semantic library here. Let me create a new library. I don't know where I kept it. I'll simply show that option, right? Configure pin swapping. Okay. So for example, let me just create a component. Okay, so you can go to configure pin swapping. So it will ask you to so here, see pin swapping. So which group of signal, which group of pins you want to do the pin swapping? Okay, assign pin swap group. So you can create a group or bus for the swapping. Okay. And part swapping, if you have multiple parts and means the same component, you can do a part swapping also. Okay. I'm just showing the feature, you can explore it. If you have any questions, you can reach us. Okay. And we have covered the feature. If anything is missed, let me ask, I'll show you. Okay. So now, so thank you all. Thank you for your time and attention. And if you have any questions, discuss now.